Hello, welcome back to the Computational Genomics Lab. We have leveled up to level 9. We have the ATACseq pipeline output, which has start and stop regions of where a peak was, which corresponds to open regions of the chromatin from the entire genome. So we're going to look at those peak files today and make a function that will import those peaks for us in the future. In case you have a lot of files, you might want a function that could just load them all at once. And we'll be making some more functions along the way in level 9. So here, let's get started. We're in masterclass lessons, level 9, import peaks. And I'm going to switch to my RStudio now, and it's the same document you all have here. So we'll need some packages here to make sure they're loaded. Again, the document will have much more text on what has happened here, max 2, how it called peaks, more information on that. But essentially, what this data is sequencing reads of regions where there was accessible chromatin, we'll get sequencing reads, and where there wasn't sequencing reads, we can kind of assume there wasn't accessible chromatin. So let's take a look at two peak files, and what we would commonly do is we have two replicates of the 0 time point or no dox treatment. We'll just find out which peaks are in common between them. That's a really handy skill to have, is to overlap intervals between two files, especially when there's like 70,000 peaks we'll see here in these files. Okay, so let's load one up. These files, if you follow the videos or the links below, are all publicly available. They're the max 2 output of the NF core pipeline, but if you didn't run it, no big deal. These peak files are there for you. You're just gonna have to change your file path to match it. But this last file name here, here is the name of the file. So that will still have the same name for you. And we're going to pretend that ES, wild type, and control don't worry about that for now. Okay, so let's load in a peak file. So here's replicate 1 of our 0 time point and replicate 2 of our 0 time point. We can look at these real quick using the view and see that we get the chromosome start and end of every peak, and each peak has a name here, a score, and it's got a number that's important. So each peak has a unique identifier, has a start and end, and which chromosome it's on. And we have these weird contigs here, these GL things. Those are parts of the genome that haven't been aligned yet, and we'll just sort of ignore them for now. I'll show you how to remove them, and you can deal with that how you prefer in the future. We can also do a head of these peak files and get some of the similar information. But it's easier to sort of look at it in the view. Each row is a peak with a start, stop, and which chromosome it's on. Okay, so now we want to find which starts and stops are the same between those two files we have here, KO 0 peaks and wild type 0 peaks. The important information is the 0 because it's the 0 time point. So if we looked at those, we saw these GL numbers. I'm not going to print them out again. But you can see them here. So we can remove those with a simple grep, where we can go into our peaks object with a square bracket index and grep for anything that has chromosome in it. We want to keep it in the seq names, which is this information here of our peak file, which is the chromosome start and stop. So this is going to get rid of anything that doesn't have CHR in it. It's going to match that character, and I'll do that for both files. And so now we can view that. And we see that those GL names are gone. So chromosomes should change here. It won't let me sort my chromosomes, but we've gotten rid of those GL things that we saw last time we sorted the table here. And we can look at how wide the peaks are. So the smallest ones are 187. The biggest one is 2,958. So there's some good information in these peak files, but most importantly, where they start and stop. And that grep got rid of those contigs that don't have a name. We're going to make a function that will do all of this, so every time we import a file, we don't have to do that over and over again for each file. So let's do an overlap first, though, and we can take a look at that. So we're going to compare the two files we have and find all the peaks that overlap. we can see, let's do that. Okay, so we're using the find overlaps function here from genomic ranges, and we're calling this object OVF for overlap frame. And we're going to take the G ranges of this 0 time point and this 0 time point and find the overlap. And we did that. It gave us a warning that we have those GL items in there, and there's 54,000 that overlap. Okay, so let's do this with our ones with the chromosomes removed. That's wild type _0 chromosome. That's where we've removed the, and we see it's pretty much the same, 54,064 versus 54,170 if we get rid of those GL things. So not a big deal. So you can either remove them or not. I recommend removing them. So we can look at the subject in the query. So @2 is the subject and @from is the query. And so we can see here that sample 1 had 53,000 peaks and sample 2 had 53,000 peaks. So that's really close. And if we look at this, we can see that with the table here, we can find out how many peaks had more than one overlap. And so we can see there was 237 with 2 overlaps. So this is just a good way to check your information. This one had 2 peaks with 3 overlaps. And so you can start to think about, which sample was which, but right now things look pretty good. And so we're going to make a function now that will simply, you point to a folder with all your peak files. So if you've downloaded them on the web for this, if you're not in the class, you'll find where that folder is, make a file path to that folder using your handy shortcut if you want on your RStudio, copy clipboard, path to clipboard. Here's where I have my peak files, and I'm just going to say, here's the path to where these go. And if we sort of look at that, I can CD to there. In a terminal, I can just go CD to that same path and do a list, and I can see all my peaks files are in there. Okay, cool. So FL is going to be just an object of all those file paths for each file in there. And so we'll do that, and we can see FL has, and it matched the pattern.broadpeak. That's the type of file we want to be using for our peak files from the Max2 program of the NF Core. If you didn't run it, no big deal, but just know that Max2 produced these peaks, and we're using the .broadpeak files. Right, so we can see that that's just a bunch of file paths here with the name of the file, and we can grep the name that we know our samples have KO control or wild type _ control. And so if we take, we can make an FL, a file list of just knockouts if we want to just select those out by going into our file list and grepping any file in here, any file path that has KO control in the sample name. So we can do that and see that it's just grabbed this FLKO is only 6 files, which is half of the files here. Okay, so we can make a pattern for this. We can say KO or is the pipe wild type _ control. Grab any file that has either of those patterns, and we're just going to make that an object. I'm still going to print it out here, but you could just now, not in quotes, put pattern, because that's an object in your environment that could go into this function. Okay, so let's make this function, and we're going to call, or here's just part of the function, I should say. I'll show you one part of the function. It has multiple functions in it. So we're going to run a function on FL simply to grab, do a string extract, which will break apart the file path name and we're going to grab object y, which matches KO or wild type. So it's going to go through that FL object and look for anything that matches to that. And it's going to, the sapply here in the front means it's going to do that for each file path. It's going to go in and look for each one. And that object then, when we extract it, can be just the sample name, whether it's KO control or wild type _ control with the time point in there. That's what the +D means, is anything else after that. Okay, so if we run that, we can see we have an object called sample name, which is giving us like KO control 0, etc., etc. Each of the names of the files. And we're grabbing that right from the file path, which is important because it's for reproducibility, that we're grabbing our sample name that's in the file itself. So if that file is mislabeled, then we might have a mistake, but we could track it all the way back to the beginning this way. Okay, so we have an object sample name, which can be important for a for loop, which is what we're going to do here. And we're going to make a function called import peaks. And that is, we're going to call it as a function using the function in R. And the inputs to this function needs to be a consensus file path. So that file path to my directory with all of the peak files in it. Okay, cool. So I've got to give you that. And then we're really just doing the same things we just walked through. So we're going to list the files in that folder and match to this broadPeak. Then we're going to make an object called sample name and grab that. And once we have this object sample names, we can use that as the index to our for loop. So it's getting kind of, it's short, but it's pretty powerful that we're listing all the files, making an object for a for loop called sample names here. And we're going to make an empty peak list before we use the sample names. Peak files. So now we're going to say we have the sample name and where the peak file is the two objects we have here with peak files and sample names. Okay, so what we can do is do a for loop for one, and the seek along is a function meaning go 1 through or for I. It's just a different way of saying it. For I in the whole length of the peak files, so our 12 file paths, do our track layer import on the peak file that is currently indexed, or the first file, the second file, the third file in that sample name and in the peak files. Okay, so, and then we can clean out the non-chromosome starting pieces of the genome with an object called filter peaks, and we can leave it with the names of the seek names as peaks of peaks as a character. So we'll have filtered out all the ones in the seek names that do not start with chromosome, basically. Okay. That do start with chromosome. So it has to start with chromosome. It'll go into the seek names of the peaks file. Okay. Oops. I didn't mean to run the function yet. Sorry. And then we're going to make a peak list. So we're going to put all these samples together, and we're going to take the first sample name and import it with the filtered peaks that just came out of here. And then we're going to repeat that for each of the file paths in there. And so you can see, instead of running all of this for each of the files, you can just do it. So it's a for loop built in here. So let's start this function here. Okay, so now it's in here. So what you're going to want to do is go back to your util folder. But if you've cloned this class, it turns out it's in here. But you're going to want to put your functions in a .r file in your util. So I'm going to go back to my working directory, which is in the wrong lesson. So let's go to 09 and set working directory because we just leveled up to here. Okay, cool. I'm in the right place. So I have this import peaks function loaded. You'll have to run that function each time or source that this file. Here's some documentation. That it's in here, the documentation already if you clone the class. Okay, so let's do something simple and use that function, which again is just simply listing a file path, going in there and importing each peak file essentially with some matching. Okay, and making a list of G ranges. So each row in the output of this will be a G range, and there'll be 12 of them for each sample, 2 replicates, 6 time points. Okay, so we're going to run import peaks, and the consensus file path parameter that's required is going to be called peak path. So I'm going to do that. And then I can also just really quickly look at how many peaks there are by using an sapply across my peaks. Once it loads, it takes roughly about a minute. But then what we can do is for each G range in my peaks, we can do this sapply function and calculate the length, which is the number of peaks in each sample, and pipe that to a data frame. So if we look at my peaks here, we see that it's a bunch of G ranges in one big list. And that's super handy. I hope you'll see why as we move forward, but just realize right now it's always good to import more data and then pick from it by matching sample names, etc. For the overlaps. Okay, so we can go through each of those G ranges now and calculate the length and make that a data frame. And let's see here. Where did it go? Okay, so here it is, num peaks, view num peaks, and we can see for each sample how many peaks there were, and there's roughly like 68,000 to 80,000 peaks. So that's good to know, information real quick that we can get from that list of G ranges of imported files, and we'll skip that. So, okay, you now have a function called import peaks, which simply we walked through each step and then we compiled it together into a function called import peaks. And now next time in the next class, we can source that file and we'll have those functions loaded up, and we'll just need to give it a consensus peak path file and maybe what pattern you want to match it to you might want to adjust. So that's all for now. You have a handy function to import all your peaks, and next we will continue making functions for overlaps between peak files. All right, see you there.